In part 4 of our study over rational functions, I actually just screenshotted a couple of the problems from the text, and we are going to work on those. So this is from section 4.1, and these are just a couple of the word problems that I liked the most that had rational functions modeling some like real world, or technically they're made up, but just some like real life scenarios. So we have a cost C in dollars to remove P% of an invasive species of Ipuzidi fish, not a real fish, I Google searched it, from Sasquatch Pond. That should have been my clue that it's not real. It's given by this very real rational function where P has to be between 0 and 100, only including 0. That's because P is a percent. The first thing that we're going to do is find and then interpret C of 25 and C of 95. So we're going to get values for them and then say in words what those values actually mean in the context of the problem. I'm not going to go super in depth on how to find both of these values because we already know how to do that. I actually have my calculator here right next to me for some real-time math. So real quick, we'll do 1770 times 25, and then I'm going to divide that by 75, and we'll get 590. Then plugging in 95, we get 33,630. All right, so that's easy enough to find those, but interpreting them is a different story. Let's see what P and C of P mean. So really, whenever we plug in a P value, we output a C of P value. Those are the like X and Y coordinates, in this case, the independent and dependent variables here. Now, P we already know is percent of invasive species of fish. So it's how much of the percent we're removing from the pond. So P is the percent of fish removed from the pond. Then C of P, as we're told, is the cost to remove that specific percent of fish. So it only makes sense that as the percent of fish that we're removing increases, the cost will also increase because we have to remove a higher percentage or more fish overall. So it looks like when P was 25, or 25% of the fish being removed, it only cost $590 to do that. But when we increased to removing 95% of the fish, almost all of the fish, it's going to cost a lot more money. Let's write that out in a sentence. Here is one way of multiple ways that you can relate the 25 and the 590. It costs $590 to remove 25% of the fish. Sure, you can use a few more words from the pond. You can put the name of the fish in front of it. You can say to remove 25% of the fish, it will cost $590. Either way is fine. Then you can write a similar sentence to interpret what C of 95 means. And that sentence can look just like below. All I did was change the numbers. So part A is not too bad. It's basically doing algebra, plugging in a number, but then also because it's an equation modeling a scenario, we actually can analyze it and interpret it using words. Now in part B, it's asking us about the vertical asymptote at x equals 100 and what that means within the context of the problem. Saying what does something mean within the context of the problem is basically the same as in part A when we had to interpret what those numbers meant using the problem, the context of percentage of fish costing a certain amount of money in dollars. So there is a vertical asymptote at x equals 100 because, as we've learned in the previous videos for this section, whatever value of our P in this case makes the denominator 0 and doesn't cancel with something in the numerator, that would cause a vertical asymptote. So since plugging in, and this should say P actually instead of x here, when we plug in P equals 100, we actually do have a vertical asymptote there. Now if we think about this, as P gets closer and closer to 100, like when we saw it was 95 versus 25, the cost went up significantly. It was going towards positive infinity. Let's take a look at the graph of this to sort of see what that means. Okay, we can clearly see that as we graph this, we can hardly see anything. This looks very strange. So what I did here was I used this little tool up here to change the minimum and maximum x values and the minimum and maximum y values because I wanted to be able to zone in on what I wanted. So I also use the step function to make the steps along the x-axis only 10, and since the y values were so large, I made those steps 5,000 instead. So now we can sort of see exactly what we want to see. And when we zoom out even more on this rational function, we can see that it has two parts. But we don't care about this bottom part because it's negative values where in a real world scenario where we don't care about we don't have negative percents or negative cost. So we can clearly see that we have a vertical asymptote at x equals 100, or p equals 100 rather, and as we try to approach p equals 100, meaning we're trying to clean up close to all the fish in the pond, 100%, our cost becomes astronomical. It approaches infinity. And that just basically means that it is not feasible to clear up 100% of that invasive species of fish. So one of a few possible answers that makes sense is to say that as we approach p equals 100, so as we approach that vertical asymptote, the cost skyrockets. We saw that it approached positive infinity. Therefore, it's not feasible or even possible to remove 100% of the fish, and even getting close to 100% is basically impossible. We'd look just like this fish up here. In part C, it's asking us what percentage of these fish can we remove for $40,000. Basically, we want to know what is P, or what percentage, will give us an output or a cost of $40,000. That means that we're going to find P, but we know C of P. So we know the cost is $40,000, and we're going to set that equal to 770P over 100 minus P, because instead of plugging in P and finding cost, we know cost and we want to find P. So what I'm going to do is basically just cross multiply. And when I cross multiply, it's like multiplying both sides by 100 minus P. So I'm going to multiply this 40,000 by 100 minus P. And then set that equal to our other cross here, which is 1,770p times 1, which is just 1770p. Then what we're going to do is distribute the 40,000. So 40,000 times 100, it's going to be 40,000 with 2 extra zeros on it. And then minus 40,000p equals 1770p. I want to get all my p's on one side, so I'm going to add 40,000p. When we do that, we'll have 41,770p on the right-hand side. And then 4 million on the left. I added those zeros there so I could see what number it was, or added the commas rather. Then we want to divide both sides by the coefficient of P. And we end up with P equals 95.76. Now P is a percent, so it says what percentage of the fish can we remove for $40,000. It looks like we can remove 95.76%. So as we saw earlier, C of 95, removing just 95% of the fish, cost about $33,000. And for $7,000 more, we only are able to remove like 0.75% more. So as we saw, it kind of loses, at a certain point, it doesn't make sense to increase the percentage of fish that we remove because the cost increases astronomically. The next example that we'll look at is number 20, and this is talking about the population of Sasquatch, so definitely not real, in Portage County, was modeled by this function P of t, and it tells us what t and P of t represent. So it says the population of Sasquatch in Portage County, so that is P of t is the population of Sasquatch, and then t is years. The reason that we know that is because it tells us t equals 0 represents the year 1803. Also, if you go back to this original time this was explained, it does explain it a little bit more in depth where t is years. So you can take a look back there as well in section 1.4. What we want to do is find the horizontal asymptote of this graph and explain what it means. As we recall from part 3 video, the horizontal asymptote is found by finding the degree of the numerator n and the degree of the denominator m. So the degree of our numerator is just 1 because it's 150 t to the first, and the degree of our denominator, m, is also 1 because it's t to the first, and then plus 15. So because n equals m, our horizontal asymptote is the horizontal line y equals a over b, where a is the lead coefficient of the numerator and b is the lead coefficient of the denominator. The lead coefficient of the numerator is 150, and the lead coefficient of the denominator is 1. Therefore, our horizontal asymptote is the line y equals 150. So we have found the horizontal asymptote of the graph of y equals p of t. The next thing that we have to do is explain what that means in the context of this problem. In the previous video, we talked about the relationship between a function, the graph of a function's horizontal asymptote and its end behavior. And the end behavior is how a graph behaves at the very ends. So all the way to the right as x, or in this case t, approaches positive infinity, and all the way to the left when t approaches negative infinity. Let's talk about positive infinity here. What we do know is that as t gets very large, so let's say values, this is when t is 0, the year 1803. Let's say, 25 years past that point at 1828, and then 50 years past that point, 100 years past that point, and so on, all these years past that point. What happens is our graph is going to level out at this horizontal asymptote. It's going to approach 150. So as the years go on, the population of Sasquatch is going to level out to 150 Sasquatch. So as t approaches infinity, positive infinity, and as the years go on, that's what that means, the population of Sasquatch in Portage County approaches 150. In this very last example, number 22, I picked it because it looks harder than it really is. I did decide to only do part C since we're not going to be graphing certain data. Now, what we see here is that we have some electrical circuit data, which is pretty cool. It's kind of like a physics engineering kind of idea. And then instead of using the table, we are given the actual formula relating power to resistance. For this circuit, it is P of x equals 25x over x plus 3.9 quantity squared, where x is the resistance, and so then therefore P of x would be the power. So resistance is our input, x, and power is our output, P of x. What we want to do in part C is find and interpret the end behavior, so find the horizontal asymptote, of P of x as x approaches positive infinity. What that means is find the horizontal asymptote, because that is what end behavior is as x approaches positive infinity. So let's take a look at P of x. The numerator is easy enough. However, the denominator is not written as a polynomial in standard form. So what I'm going to do is multiply this out to see what it'll look like in standard form. When we multiply our denominator out and we do x plus 3.9 quantity squared, we'll have x squared. Then we'll have plus 3.9x plus another 3.9x, which will give us plus 7.8x. And then we'll have 3.9 times itself, which is 15.21. Now, we did not really need to get those second two terms because really we only care about the leading term, but I just wanted to show you what it could look like multiplied out. All right, in order to find the end behavior of P of x, again, we need the horizontal asymptote. So we need to find n and m. N, the degree of the numerator is 1, and m, the degree of the denominator is 2. Because n is less than m, the horizontal asymptote here is actually the x-axis. It's the line y equals 0. Now, what does this mean? If we take a look at the graph, and remember x was resistance and the output y, or P of x, was power, as the resistance increases and increases or approaches positive infinity, we can clearly see that the power output approaches 0. It approaches the x-axis, our horizontal asymptote of y equals 0. And this makes sense because as our resistance increases and increases, we're not able to output any power anymore, or a power that's approaching 0. So we can write that as resistance increases, which means as x approaches positive infinity, the power generated, or P of x, approaches 0.